Welcome back for video 3 of our kinetics tutorial. This video is going to start with a little bit of summary problem solving, and then we're going to delve into one last detail of sort of the mathematical end of dealing with rate laws themselves. So first off, this is actually a problem from the midterm that I gave last semester on kinetics, back when it was still part of the Chem 121 curriculum. And so I asked students to go through and figure out, based on these data right here, what the differential rate law was, and to then determine the rate constant k. And then we did a few other things from there. So first off, looking at the data and trying to figure out the differential rate law, we saw two ways we can do this. One of them very mathematical, the other one a little bit less so. We'll go ahead and start with the less so method, which is that if I look at the rate at which the factor by which those two are different from one another, it is a factor of 1.5. And if I do the same thing with the rates that are provided, all of which, or at least the first two of which, are 10 to the minus 4 molar per second, what I find is that we've had an increase of 2.25. That's how much bigger we've now gotten in terms of the rate. So with that knowledge, we actually can skip over the next experiment because it's not going to tell us anything else that we don't know. And noting that it's 1.5 and 2.25, maybe you readily recognize that this is 1.5 squared. If so, good on you. But what we do know for sure is this. Changing the concentration of A definitely altered the rate of the reaction. And it definitely didn't alter it by the same factor. It altered it by a larger factor. So even just from that, we can feel pretty confident that this is a second order reaction. But if we really want to prove it to ourselves, just go ahead and take 1.5 and square it. Put that into a calculator. You will see that it comes out to 2.25. And so from there, you might remember that to get k, we actually need to write the differential rate law, which is going to be rate equals k times a squared. And so now if I take any one of these, and it shouldn't matter which if I have the right rate law, if I plug in the rate and the A concentration, I should be able to get it. So we'll go ahead and take that first set then. 0.12 molar, sorry, I'm doing that wrong. 3.89 times 10 to the minus 4 molar per second is going to be equal to K times 0.12 molar squared. And so to solve for that, all I need to do is divide both sides by that squared molarity, and we'll get a value for K. And that value comes out to be 2.7 times 10 to the minus 2 molar to the minus 1 seconds to the minus 1. Again, notice the funky units. If I take that number and I multiply it by 2 molarities, I'm going to wind up with molar per second, just like I should. Now, the next question was circle the graph that would be linear based on your answer to part A. So, I'll give you a moment to think this through. Pause if you need to. And now that we're back, it should be that one. Because, again, this is a second order reaction based on what you saw, and what we observed is that this is the linear graph if I'm dealing with zero order. That's it if it's first order, but this over here would be for second order. Now, C, D, and E are all going to make use of the individual rate laws. We've now figured out essentially that the integrated rate law would be the one with reciprocals in it. In other words, it would be 1 over A equal to 1 over C naught plus KT. Well, now that we have that, if we start at a new value, a new A value, we can work out anything we like. The first question asks for the initial reaction rate, and it's worth recognizing here that the different rate laws we have do different things for us. The differential differential rate law, you might recall, gets you from rate to concentration. The law that we have right here, the integrated one, gets me from concentration to time. And so the two rate laws do two different things. So if I know that I've got the concentration here, I'm starting in the middle. I just want to use whichever one makes the most sense right now, and so I'll go ahead and use, since I want to get to rate, the differential law. So to get this rate, I merely need to plug in what I have. We've got the K up here, 2.7 times 10 to the minus 2 molar to the minus 1 seconds to the minus 1, and we just need to multiply that then by 0.50 molar squared, giving us a value of 6.7, actually 6.8 I should say, times 10 to the minus third molar per second. Okay, so there is my reaction rate, and I can get the rate from the differential law. Now the half-life and the rate 5 minutes later are going to require some different kinds of machinations. Half-life is something we need to define, so we're going to skip that for the moment. I'll come back to it just a second afterwards. But this reaction rate 5 minutes after the fact is a little different, because you'll notice I'm giving you a time, which is right there, but I'm asking you for a rate, which is over here. So we're going to need to use both of our pieces of information in order to solve this. I'm going to grab a new piece of paper so I don't have to write too tiny. Since we're dealing with second-order reaction kinetics, the first thing I'm going to do is deal with the integrated rate law, because I've got the time. What I don't have right now is an actual rate or a concentration at that time. But I can get it from here. I can make that connection. Because 1 over A is going to be equal to 1 over the initial A, which we saw was 0.50 molar, plus K times the time. And so my K, being 2.7 times 10 to the minus 2, molar to the minus 1, second to the minus 1, times the time, which is 5.0 minutes. Now, of course, I'm going to have to do a little something with that. I've got to actually multiply that by multiply that by 60 seconds per 1 minute in order to get myself something usable here. But when all of that is said and done, what I now have right here, 1 over 1/2 is going to be 2.0 molar to the minus 1 plus 8.1. And again, you'll notice that the units are again going to be molar to the minus 1 because the seconds cancel out there and the minutes cancel out here. And so that is going to be 1 over A. In other words, 10.1 molar to the minus 1, which means that my A concentration at the 5-minute mark is the reciprocal of that. That reciprocal being 0.099 molar. Now that I have that, I can do the same thing that we did in part C, which is determine the reaction rate on the basis of that by using the differential rate law equation. And so again, we're back to rate equals K times the A concentration squared. That is again 2.7 times 10 to the minus 2, molar to the minus 1, seconds to the minus 1, times our new concentration of 0.099 molar. And again, that is squared. The first one's going to cancel that. The second one is going to give me the molar on the top of the rate. And when all is said and done, what I wind up with here is 2.6 times 10 to the minus 4 molar per second. So not too shabby here. We can make use of both of those equations in sequence if we need to in order to come to a result. Now, beforehand, there was one more thing we couldn't answer, and that was the half-life of this reaction, because we actually don't quite know what that is. So let's delve into the PowerPoint, shall we? So one of the things you can do once you've got a reaction's rate law is figure out what its half-life is. And all that the half-life is the time necessary for half the reactants to be consumed. It's very likely that if you've heard this this phrase here, anywhere other than a video game title, it is probably in nuclear chemistry. It's the way that most isotopes are defined, is what is your half-life? How long do you persist? And so if we want to figure this out, it really is just a concentration versus time sort of thing. So again, we're going to be working with the integrated rate law. Here, for example, is the integrated rate law that we came up with for a first order reaction once we solved it for the actual x value, that exponential decay. Now, all I'm going to do in order to determine the rate law is a little bit of substitution and then some algebra. In essence, I'm going to call the time t1/2, little subscript 1/2, that's not multiplicative. Once I've done that, what I know is that at t1/2, I will have 1/2 as much of this stuff, the x, whatever it might be, as I originally had. I started at C0, now I'm going to be at 1/2 C0. Once we plug those things in, there's nothing more to it than just simply solving for t1/2. And so the first thing we can do on this one for a first order reaction is note that the C0s cancel out. And once that happens, I'm down to a much simpler equation, and we see that t1/2 and k are going to have some sort of dependence on each other. If I take a natural log in order to undo what's going on here, natural log of 1/2 will be negative natural log of 2. And of course, natural log of e to anything is just that anything. And so now with this, if we divide both sides by negative k, we wind up with our result. So ln of 2 over k is how you determine the half-life for anything that is first order. Bear in mind that for other reaction orders, it's going to be a different expression because of the fact that we don't actually have the same math going on. In this case, we had a natural log that allowed us to cancel out the C naughts. The nice thing about this here is that you'll notice that as long as I don't mess with temperature, which could potentially change K, T1/2 for a first order reaction is a constant. And so that should give you a clue when we get to nuclear kinetics later on in the class. Since half-lives are tabulated for nuclear isotopes, that must mean that nuclear kinetics are first order, because otherwise they might depend on something else. But here we've got just a simple inverse proportionality. The faster the rate constant, the quicker, the shorter the half-life. If I'm dealing with a second order reaction, I'm just going to do the same process with that rate law. So here we have 1 over x giving me kT plus 1 over the original concentration. Here again, I will plug in C0 over 2 and T1/2 into those two spots where I had variables before, and now we're just solving for T1/2. Note that 1 over C0 over 2 would just be 2 over C0. And so if I subtract off that 1 over C0 from both sides, I should wind up with just simply 1 over C0 on the left. And once I divide through by my K, here is the expression I get for T1/2. Notice there's a difference here. With a second order reaction, I now actually have a dependence on the initial concentration. And on some level that should make sense. If I'm dealing with first order kinetics, the rate slows down at the exact same speed that I lose reactant. And so for any chunk of time, I'm always going to be destroying, if I look at a 5-second span or a 10-second span, I will always be destroying the same percentage of stuff each 5-second span or each 10-second span. Or in this case, each half-life. Because for first order kinetics, it's a proportionality. If I've got half as much stuff, I'm destroying it at half the speed. That is not true for second order kinetics. For second order, I can see now that the concentration's involved because as I destroy stuff, the rate responds a little more vigorously than it does in the first order sense. Once I've destroyed half my material and gone through one half-life, my concentration's now half as big, but my rate is 1/4 the size it used to be. So what's going to happen is as I destroy more and more stuff, the half-lives are going to dilate. They're going to get longer and longer and longer. I would encourage you, with a little bit of time later on, to try and do this for a zero order reaction. Remember that the rate law for that one was simply that x equals C0 minus kT. See if you can go ahead and figure out what the half-life is there, and I would encourage you to surmise right now whether you think that the half-lives will be constant, get longer as time passes, or get shorter as time passes for something zero order. All right, let's go ahead and finish this up with a couple of problems. So this one here involves a reaction of hydrogen peroxide decomposing into water and O2. If you've ever wondered why it is that if you have peroxide in your medicine cabinet for disinfecting, that it gets less and less effective as time goes on, it's because every time you open the bottle, you outgas all the O2 that it has produced and then allow it to continue this reaction on and on and on and on and on. You'll notice that under certain sets of conditions, you can have a pretty darn quick half-life. And so we're going to look at a set of conditions where at 0.3 molar H2O2, the reaction's first half-life is 72 seconds. So the first thing we're going to do together is try and figure out the rate constant if this is a first-order reaction and the rate constant if it's a second-order reaction. So as we saw earlier, different rate orders beget different integrated rate laws, which beget different half-life formulas. So to figure out what K would be for first or second order, we just simply need to plug it in to what we know into the expressions for both of these. So for first order, it's pretty straightforward. ln of 2 over K is equal to my half-life. If I want to solve for K, I'm just multiplying K on both sides and dividing T1/2, and I end up with ln of 2 over T1/2 equals K. And so now I can plug in what I know, ln of 2 over the T1/2 that was provided in the problem of 72 seconds. And my result is going to end up being 9.6 times 10 to the minus 3 inverse seconds. Notice how the units in this case are inverse seconds because the second is the only unit that appears. Follow the bouncing units. For second order, I've got to put in one other piece of information from the problem, and that's that this is going to be 1 over now t1/2 times c0 equals k. And so I now need not only the 72 seconds, but in addition, the c0, which was 0.300 molar. And so you'll see again, we're going to wind up with the molar to the minus 1, second to the minus 1 units, and the number we come out with is going to be 0.046. And so depending on how this particular reaction behaves, we're going to have one of these as our K value. But we've got to figure out which one that is, and so luckily the problem has one little bit of assistance for us on that front. So that assistance is that it's going to now tell us that the second half-life, the amount of time it takes to destroy half the stuff after the first half of the stuff has been destroyed, so getting down to 1/4 of what we began with, also takes 72 seconds. And so here are the questions I have for you. First off, is the reaction first order or second order? Secondly, can you write the differential and integrated rate laws for the reaction based on that answer, assuming that the rate is entirely H2O2 dependent? Lastly, I want you to try to tell me, how long would you have to wait from the original starting point before the rate of the reaction dropped to 1.0 times 10 to the minus 4 molar per second? Those are all going to be things you can find on the Canvas quiz that I told you about way back at the beginning of the first video. This will be the first problem. We're going to have a few others that come up over the course of the last 2 videos. See you then to do a little bit more conceptual stuff involving what rate laws tell us about the microscopic picture of how a reaction takes place.